Hi, everybody. Thank you very much for coming. This is a great turnout. I'm really excited to introduce, for the second time this week, Chris Kapulkin. Chris is visiting us from the University of Western Ontario, where he's been for quite a while at this point. Did his PhD at the University of Pittsburgh. Chris is a homotopy theorist by training who happens to do a lot of different things that connect to a lot of different areas of math. So yesterday we got the homotopy theory as applied to type theory talk. And today we'll get the homotopy theory as applied to graphs with connections to data science. So pick your favorite area of computer science, and Chris is connected to it somehow, despite not claiming to be a computer scientist himself. On a more personal note, I think sometime when I was a PhD student, Chris invited me up to Western Ontario for my first invited seminar talk, as far as I remember. And so I'm excited to finally return the favor many years later. So thanks for coming, Chris. Take it away.
Thank you so much. Okay, so yeah, as Rob mentioned, I'm a homotopy theorist, and I'll tell you in a second what that means to me. And I recently started thinking about applying homotopy theory to graph theory, and that's a topic that was studied quite exhaustively, and I put some references here. But essentially, I feel like we made some headway with the techniques coming from homotopy theory, but what we really want to do now is to find people who know graph theory and can write algorithms to ideally put some of the stuff that we did into actual practice. So I have two versions of this talk. One is chalk talk, which that's the version. The other one has slides. The one with slides has no math in it, and it's essentially pitching to finance people. And I hope to get to the applications to finance towards the end of the talk. I was told that I should not dress like that when I pitch to finance people. And apparently I look like I'm homeless. But I feel like for a mathematician, that's like pretty much halfway there to the department chair. Yeah. Okay. So here are some references. So discrete homotopy theory, the maybe flavor that I'm going to talk about, goes back to the work of Atkin from the 1970s. Atkin was a physicist at Oxford, and he was interested in analyzing networks. And the particular network that he was concerned with was a social network. He was looking at different committees in his department, and he was worried that some people are becoming too powerful by being on several different committees. Now, as someone who was in like director of graduate studies role, my experience has been that getting people to do any committee work is pretty much impossible. So the idea that you would worry that some people would be too powerful because they will be on too many committees is just something I cannot relate to in any way. But so that happened in the 70s and was in some way forgotten until Reinhard Laubenbacher was approached by the DoD to kind of build a proper mathematical foundation for this work. And that was, I think, related originally to the Operation Desert Storm, where, again, some things were analyzed and you wanted to know where the enemy is so that you can prepare for it based on some incomplete data. And my, let's say, recent contributions to this field are in two papers with two excellent students. So Daniel Carranza, who's now at Johns Hopkins, and Nathan Kershaw, who's a PhD student at the University of Western Ontario. Okay, so if you like anything that you're hearing, these would be the papers I would try to Google. Okay, so let me first tell you something about homotopy theory. It's going to be very quick. But just to give you a sense of what I'm doing, I'll just give you the definition of a homotopy. So if I have two continuous maps, so let's take FG to be two continuous maps, X, Y, continuous maps. And these are continuous maps between topological spaces. If you don't know what a topological space is, it's just some geometric object, and a continuous map can deform it, but cannot rip it in any way. Stretch, you can squeeze, you can do a lot of other things. So a homotopy between them, homotopy from F to G is a map H defined on this product 0, 1 to Y, such that when I take H and I plug in 0 in the second coordinate, I get F, and when I plug in 1 in the second coordinate, I get G. So the way I would picture it is, if my X here looks like this, by taking this product, I'm building a cylinder here that looks like this, and my Y, as always, is a potato. So this is X times 0, 1, and H is a map like so. And now when I look at the top part, so maybe part corresponding to 0, so this is over here X times 0. On this part, I see F, and on the bottom part, here when I have X times 1, I see G. Okay, and so H, I think of it as a continuous deformation of F into G. And one definition that I get from that is that I can now talk about two maps being the same, but they are not necessarily equal, but they can be deformed to one another, and that motivates a subsequent definition, namely a map F X to Y is a homotopy equivalence. Homotopy equivalence if there is a map G from Y to X with homotopies. So G composed with F should be homotopic to identity on X, and F composed with G should be homotopic to the identity on Y. So essentially, I took the definition of a homeomorphism or bijection, and I replaced equality with homotopy, and that's a new notion of sameness that I want to study. And maybe I'll say that the goal of homotopy theory, so if you ever meet a homotopy theorist, that's what they want to do in life, is to classify nice spaces up to homotopy equivalence. Now, they do it in a somewhat convoluted way, and when you maybe if you open the paper in homotopy theory, it might not be apparent that that's what's happening, but in a way, this is the overarching goal. Okay. So that's a nice idea. The idea of having a homotopy, a relation on maps that's somehow weaker than equality, and then having homotopy equivalence and saying that I can take two objects and try to classify them up to this notion. It's a fascinating problem for which we develop a lot of tools, and these tools could be reapplied in other contexts. So, okay, this is not a homotopy theory seminar, however, and so my question would be, can we do something like this? Something like this for graphs. Okay. Oh, sorry. The last definition, perfect. I'm going to take 1 point, and I'm going to take Rn, n-dimensional space. They are homotopy equivalent, shockingly. It should be shocking first time you see it, because this one seems bigger, right? So the size actually to a homotopy theorist doesn't matter. You can have spaces that are very small, but they are very large in some other ways. So here I can embed this at the point 0, and here I can embed I have just one map to the point, right? And now, if I do this round trip, that's of course identity, right? So all I need to do is I need to convince you that the identity on Rn is homotopic to the map that picks 0. So let me draw a picture. We can also write a formula, but let's not. I'll draw a picture. So I need to contract everything to this point. What am I going to do? For this point, I'm just going to traverse things over here. For this point over here, I'm just going to traverse things like this. And I can just squeeze the whole space to a single point. One thing that I wouldn't be able to squeeze to a point, I'll give you another example. If I have a point, I can also just draw a circle. And so it's hollow inside. So if I try to do it, there will always be a hole inside, and I will never be able to fill that in. So these two are not homotopy equivalent. Okay. In some sense, what this amounts to, this is a huge oversimplification, but I'm trying to find n-dimensional holes in my space. And we're going to apply essentially this idea to graphs in just 1 second. Good? Okay, great. So can we do that for graphs? So kind of naively, when I look at a graph, I can think about it geometrically. I can kind of naively say, well, graphs are one-dimensional spaces. So yeah, sure, let's apply it. I don't get anything interesting this way, right? So for instance, let's see. If I have this graph, it should be the same as this graph, right? Like it's just one hole inside. I can just stretch this maybe like this slightly flatter, and this is the same as this. This is the same as, and so on. Maybe I can also look at something like this that would be the same. Like things without any holes would all be the same. And so on. So actually, this is boring. Why is it boring? Because all you need to know is the number of vertices minus the number of edges, right? And if you look at the examples I'm giving here, this one number completely classifies graphs in that way. Okay, so that's not interesting from our point of view. But maybe there is still something that we can try to do with graphs that would capture not this topological information, but something of more combinatorial nature. So let me try to do that. Okay, so if I'm gonna do that, I need to figure out how to mimic the definition of homotopy that I wrote here for graph theory. So there are a few questions. In fact, maybe I'll underline the symbols that I need to explain for graphs in order to make sense of the definition. So the first thing is, what is this interval in the context of graphs? How do you make sense of the unit interval, like a topological space that's 0, 1, in the context of graphs? Second, how do you make sense of the product? There are many products of graphs. Which one is the right one? Or maybe there are many right ones. And lastly, what is a graph map? Pretty much everything that's not X or Y is up for grabs, right? So I need to make sense of these three objects in order to define homotopies of graphs. So that's what I'm going to do. I'm actually first going to tell you very quick. So for me, just to fix notation, a graph is a set with a symmetric and reflexive relation. Okay, so something that I would depict maybe like this. Okay. So symmetric meaning the edges are undirected. There are no multiple edges since it's a relation. And lastly, there are those little loops on every vertex. They are so small that you can see them because I didn't draw them, right? So every graph is they are reflexive. Okay, and a graph map is a function preserving the relation, right? Okay, so let me just give you a few examples of graphs just to introduce some notation. These examples will be with us kind of for the rest of the talk. So there is a graph that looks like this. It has n plus 1 vertices starting at 0, and they are arranged on a line. There's also the infinite version of that graph, and I know that that might be upsetting. So for me, as a homotopy theorist, infinite objects are kind of very common. But when I first talked to graph theorists and I said, that's a graph, they're like, that's not a graph. It's infinite. How can it be a graph? So for me, it's a graph. It satisfies the definition of a graph. Sets need not be finite. Okay. And the last one, maybe I'll do this. I'll just that's here. 0, 1, 2, 3, and n minus 1. Cn is the n cycle. So just a quick example. So how many graph maps are there from I1 to C4? It's a good quiz question to how many maps do we see? Usually the first answer is wrong. That's been my experience. My first answer was obviously wrong.
If you're requiring that the relation be preserved, why is that an isomorphism? What does it mean to preserve the relation?
So if two nodes are connected by an edge, then they must be connected by an edge in here.
But not conversely.
No, I don't need to reflect the relation. So sorry. So how many should there be? What? So I could pick any edge. So 4 is not right, but 8 is also not right. Yeah, it's more. It's 12. Because remember, my relation is reflexive. So there are those things that are invisible, right? So I can also take the whole edge and just smash it into a single vertex, right? So there's 12. I can pick any edge and I can pick it in two ways, this way or that way. And then I get, okay. So this was a trick question on top of a trick question, right? Like, it's like a double bluff. But it's like, yeah. But yeah, that's fun to see. I'm sorry. Yeah.
To clarify, that I understand, I'd like if you were trying to construct a graph map from C4 to I1, what would it mean? Is it possible to preserve relations because you have fewer nodes?
So from C4 to I1, oh my God, I have no idea how many maps there are. These ones I just checked on a computer, but C4 to I1. No, so it's actually easy. So I1 happens to be a complete graph, right? So any set function between the sets of vertices will be a graph map because any two vertices are connected by an edge. So this has 4, this has 2, so it's 2 to the 4. So I think nobody knows. Yeah. This is still open. Okay, great. So I told you what. Oh, I'm sorry. I'm sorry.
So I don't like subloops. Like, is it important for this theory that I imagine that?
Yes.
Yeah.
I'm sorry. I feel more Canadian now than. Oh,
It was a joke.
oh, computing 2 to the 4. It wasn't this serious. Yeah. No, it was just yeah. My yeah. Okay. So now I need to tell you something about the product. Oh my God, I really caused offense with
He really hates self. He also has to go teach.
Okay.
Don't take it personally.
Oh man.
Some
Okay.
of us are friendly to self. So it's okay.
Okay. Okay, the box product of two graphs x and y will be the box product. So I'll write it as a box. Has vertices. So it's going to be just the product of the sets of vertices. And then I'm going to say that vertex xy is related to vertex x prime y prime if and only if x is equal to x prime and y is connected to y prime, or x is connected to x prime and y is equal to y prime. And I think this usually causes some offense because of how do you parenthesize it. So I think that's the correct way of parenthesizing it. Okay, let me give you an example. So what happens if I do I1, box I1? So I'm doing something like 0, 1, and then 0, 1. Okay, so this should have 4 vertices, 0, 0, 0, 1, 1, 0, and 1, 1. And now I connect them if the first coordinates are equal and the second are related. So first coordinates are equal, 0, 0, and then the second one are related. So this is good, 1, 1. So this is also good. Now the second condition tells me the second coordinates are equal and the first are related. That gives me those two. But bless you, there are no diagonals because that would mean that x is related to x prime and y is related to y prime. So this just is C4. So that's the notation, right? It's
And we're related
is
previous definition.
is the relation of the
I see.
yeah, I know, but also yeah, it's gonna be good.
Okay.
It's gonna be good. But now I can just repeat the definition of homotopy. I have a product, I have something that looks like an interval, and I have something that tells me what a graph map is. So so if I give myself two graph maps, f and g, x to y, are graph maps. So a homotopy from f to g is a graph map h from x box in to y, such that h of x0 is f of x, and h of x1 is xn is g of x. Okay,
And what's the quantification on n?
and for some n.
Where is the first up?
So a homotopy from this consists of a natural number n together with a graph map on this. Yeah.
So if you box with I1 and Noah, just like the original picture where it's like a cylinder where you have like copy.
Right.
So then here, what's the significance of n? Like why do you
Okay. Yeah, that's a great question. So let's answer this question in my favorite way of addressing students' questions in class, which is homework problem. No, no, but exercise show that this is an equivalence relation. Equivalence relation, meaning two maps, like the notion of being homotopic is an equivalence relation on the set of maps between x and y. So I need, for instance, n equal to 2. If I have two things connected by edges, I need to know that I can still connect the, like if I want to prove transitivity. The relation wouldn't be transitive if I only had I1, right? So in a way, I'm starting with I1, and then let's say I want this property of it being an equivalence relation. So you can say, well, let's take the smallest equivalence relation that contains the relation of being like I1 homotopic. That's it. Cool? Okay, great. Okay, so one thing I'm getting for free is the notion of homotopy equivalence. Namely, take the definition I already gave you, replace continuous map by graph map, and just repeat everything word for word. Like, you know what a homotopy is, you know what the identity map is, you can just repeat this definition first. Okay, so let's figure out if there are things that are homotopy equivalent. So for instance, I have a canonical map from IN to I0. So I just smash everything to a single point. I claim that this map is a homotopy equivalence. Why is it a homotopy equivalence? Well, to be a homotopy equivalence, I need to have a map back such that both composites are homotopic to the identity. So my map back will be the map that picks 0, right? This is just a single vertex. So a map from here to here just picks one vertex here. This has vertices from 0 to n. And I'm picking 0 because that's probably the easiest. So then the round trip going like this and then back, this is the identity because this has just one vertex. So there's only one map from it, from any graph to this graph. But the more interesting one is the round trip going like this and then coming back. This is the 0 map, and I need to establish that this is homotopic to the identity, right? So smashing all of IN to 0 is the same as the identity. How am I going to do that? Well, there's a very good homotopy. I need to write a homotopy. So something that will look like this. I'm just choosing this n here to be the n of this to IN, such that when I restrict to 0 here, I'm going to get 0. And when I restrict to n here, I'm going to get the identity. And the map that I'm going to choose is the minimum. You can check that this is a graph map and that this gives me a homotopy. Like if I plug in to minimum of the two 0, then I'm going to always get 0. If I plug in n, I'm going to get whatever the other component is. So this is a valid homotopy from the 0 map to the identity. So I'm done. Great. Questions?
What is the difficulty imagining the case where it's not equivalent to just counting how many connected components there is?
So that it depends on the number of connected components. Yeah? Okay. Let me give you an example of a connected graph that is not homotopy equivalent to a point. I mean, you might object to it being a graph, but I infinity is a great example of a graph where this map is not a homotopy equivalence. Okay, why is that? So again, I can choose any map back, like this is infinite, so I might as well choose 0, right? And now let's say that there is a homotopy from I infinity box IN to I infinity, right? Like from the 0 map to identity. Okay, so such a homotopy would be defined on this, like this I infinity goes in both directions, like infinitely, like so. Okay, and like I have like a few things here, and then this thing has length n, right? Okay, so if there is such a map, then this map would have to send everything on the top to 0, like so, and everything, and I have these things connecting, right? Over here, I sent things to the identity. So 0, 1, 2, 3, -1, -2, and so on. But in particular, so I'm labeling vertices here by what they are sent to by this map. Okay, but at some point, I'll get to 0 here, and let's say n+1 here. So having such a thing would mean that I can connect 0 to n+1 in I infinity with a path of length n. That's a contradiction. That IN is finite, yeah. Okay, so let me give you 2 more examples of things that are contractible before we, yeah. Okay, so C3 to I0. So contractible means homotopy equivalent to a point. So this is a homotopy equivalent, and in fact, every complete graph is homotopy equivalent to a point. And again, if I need to draw it, I would draw it, well, on top I put 0, and on the bottom I put the identity. And I get something that looks like this. And since C3 is a complete graph, all of these are well defined. It gets more interesting when we get to C4, because now I can't play the same game. Because what happens is, if I try to play the same game, so I draw a cube, let's say that's going to be my cube. I put zeros on top, and then 0, 1, 2, 3, like so. There's a problem. Where's the problem? Yeah, that edge looks suspicious, right? There's no edge from 0 to 2 in C4. What am I going to do? Yeah, just cut it in half. Yeah, so this is, I usually like to say, yeah, if at first you don't succeed, abandon all evidence of trying. But here, actually trying again makes sense. By the way, this is only the second best answer, the second best ending to this. If at first you don't succeed, skydiving is not for you. Okay. Okay, so what I'm going to do is I'm going to fold my square into 2. So I'm going to get something that looks like this, and now all the edges are there. Okay, what do you think about C5? What? Okay, so first, is it a homotopy equivalence or not? Let's just take a poll. I love to do that. I love to see the answer. Like, yeah, who thinks that it is a homotopy equivalence? Okay, who thinks that it isn't? Okay, it went like Florida 50-50. Great. No, I think I'm 20 years late with that joke. I'm sorry. I'm Canadian. I need to update my stereotypes. Okay, so C5, this to I0 is not a homotopy equivalence. And unfortunately, I can't prove it to you in detail, but I'll give you a sketch of ideas involved in that. So in order to prove that, we need something called homotopy invariant. So homotopy invariant is some kind of assignment to F, some kind of assignment F of, to a graph, I'm going to assign maybe a group or maybe something else. I don't want to, like, some kind of algebraic object such that if X is homotopy equivalent, so this is homotopy equivalent to Y, then F of X is isomorphic to F of Y. Okay, so in this theory, what we're trying to do is we are trying to find a lot of homotopy invariants, a lot of things like F, such that if two things are homotopy equivalent, then the invariants are the same. And so the way we use it is the invariants are different, therefore the two graphs were not homotopy equivalent. And the first such invariant, so this is named after Atkin, is the fundamental group of a pointed graph. So a pointed graph is just a graph where I just choose one vertex as the distinguished vertex, and it's denoted A1 of x, and I just distinguish one vertex x0 in it, and this is the group that consists of maps from I infinity to x, f, such that f of n is equal to x0 almost everywhere. And I have the quotient by the relation of homotopy. Okay, so what just happened? I'm taking these infinite paths, you might say, in my graph, but rather than looking at, they are not completely arbitrary. There's only finite range where this is interesting. And outside of that range, it's just x0, 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 and so on. x0, x0, x0. Okay, so I could equivalently say I'm just taking finite paths. But when I take finite paths, it's less clear what it means for them to be homotopic, since you have to have the same domain to be homotopic. So I can add some padding at the beginning or the end. Doesn't matter. There's a way of formulating it. If I try to formulate it using finite paths, that would be the end of the talk. As in, I would need to take that much time to make it formal. And since I'm trying to tell you about some other stuff, I'm just gonna. So a few things. This is a group. This is a group that detects something interesting. So why is it a group? Well, if I have this interesting area over here, right? Like this is my map from I infinity to my graph X, and I have another one, and it's interesting over here. And the way I multiply them, maybe something else here. I'll go the other way. The way I multiply them is I'll do this. I'll take this. So this one I did this way, and then I put this one here. Okay. I just stack the two interesting areas, and now we can ask, okay, but is it that I take this one and put it at the end of this, or is it that I take this one and put it at the end of this, right? The numbers might not match. The thing is, it doesn't matter. I quotient by the relation of homotopy, so they will all be homotopic. So this is a well-defined group operation. It is a homotopy invariant. And when you run it, you find out that A1 of C5 based at 0 ends up being Z. In other words, when I look at these paths in C5, I can they correspond to how many times I looped around this cycle, right? Like one path would just go 0, 1, 2, 3, 4, and then 0, and then stay constant. Another would be 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 0, and then constant, and so on. I can also go backwards, which is how I get the negative numbers. And so, yeah.
These have to be like based.
They need to be based, and I'm really sad that someone pointed it out. Yeah, doesn't matter what the base homotopy is. Just let's not think about it for this talk. But yeah, they have to be based. Yeah. So when I do it for C3 based at 0, for instance, I get 0. So somehow this group detects that there's a large hole in my graph, but it doesn't see the small holes. And the way you would prove this fact is actually, if you took an algebraic topology course, you take almost verbatim the proof from Hatcher. It's quite surprising, but you develop the theory of covering graphs, and it works. And if you haven't taken a course like that, then you're lost. Yeah.
I don't want to knock you off course, but I'm not a mathematician. I don't have the aesthetic of a mathematician. I do graph theory in terms of algorithms. So you just told me that C5 and C3 are fundamentally different.
Yeah.
So why should I be interested then? I mean, doesn't that sort of what's interesting about that difference?
Great.
Aside from the fact that it's mathematically true according to these definitions, why is this capturing? Doesn't that? I mean, that makes me think.
Makes you feel like it's wrong.
It makes me wonder about what it's capturing about graphs that I should be interested in if I'm not a mathematician.
Great. Great. Okay. So, okay. So, I'll just say, if you were a
I'm not
mathematician,
a finance person either.
very good, very good, very good. Okay, so maybe yeah. Okay, so originally the theory was developed by Atkin to study social and technological networks and how they communicate. But maybe, like, what I'll say is this. So this detects what I would call large holes in graphs. And so large means 5 or larger. Okay? But
And maybe your answer could also, now I'm sounding like I'm talking to a student, but I mean, can you relate this to graph minor theory? Which
that's a good question.
Holes,
right.
but in a slightly different way.
Yeah, so that I don't know. I haven't looked into that. And
Okay.
like I know it's a question that comes up and it's
Yeah.
something we it's on the agenda, let's say. But
Sure.
yeah. I'm not sure of any yeah. But let me give you 2 more. Oh, sorry. Okay, I'll get yeah.
Is it related to the connected components?
Strongly connected
Oh, yeah.
strongly connected components of a diagram. Well,
We're doing undirected graphs.
we're doing undirected graphs, so that's one. But in fact, there is a relation. So we were working with people in medicine, and when you have this directed graph, you can, in fact, take the poset of strongly connected components, and when you have a poset, you can assign to it a simplicial complex. Out of the simplicial complex, you can build a graph, and on a graph, you can compute the invariants that I'm trying to talk about here, and turns out that these invariants predict something about the directed graph you started with. So that has a relation to, that's related, like the way we started even thinking about it, these were gene regulatory networks that, yeah, so somehow, the larger rank of these groups, the more robust your network is. And it turns out that it's higher in biological networks, like evolution tends to select for robustness. That was an interesting application that we discovered in a way using this theory. But let me give you 3 examples of something. Okay, so I'm going to take another graph, and I'm going to take a square like this, and I'm going to put 1, 2, 3, 4 things. 1, 2, 3, 4 things through it like this. So this is a square. This should have a lot of vertices. I'm going to say 6 here, 6 here, so 36. But then I'm going to make some identification. So I'm going to identify this vertex with this vertex. And I'll then identify this one with this one with this one. And I'll just do that around so this should be probably 11. So I'm going to end up with 11 here. So I kind of identify this side of the boundary with this side of the boundary. Okay. I don't know. Are there any topologists here that almost? So what should I write for the fundamental group? Yeah, this is Z mod 2. So somehow like there is this large cycle of length 5 here, but it's kind of twisted, and the Z mod 2 sees this twisting. Okay, I'll give you one other example, okay. So I can make one tiny modification to this definition, and I actually wasn't planning on talking about A2, but I can talk about A2, and that would only require making this tiny change. So now I'm probing my graph with things from like this infinite grid, and again, I'm requiring that I'm only interested on some finite region. Okay. So I'm going to take the following graph. I'm going to take a vertex here. I'm going to connect it to 4 vertices here. I'm going to take 4 more vertices here and 1 here. Okay. This thing. Now, this doesn't have any, like all the one-dimensional holes are of size 4. So they are all like C4. I should not have any A1. I should not see that. However, this A2 of this graph will end up being Z. So I can see a 2-dimensional hole inside of this data. Like the way you would think about that, like this, if you can see this drawing, I would say take an octagon, like just an octagon, and then take a north pole, south pole. Connect north pole to all the even-numbered vertices, connect the south pole to all the odd-numbered vertices. This ends up having, the only proof of that I know is a computer computation.
Not the smallest pole that dimension, like how C5 is the smallest pole.
Another great question. I believe so. I don't have a proof. But okay, so some things that we can do with this is we essentially can yeah, okay. Let's see if I can try to do something. Okay, I'll do something very brave here, and in 5 minutes I'll try to tell you what cubical homology is. And once I try that, you'll see why that was very brave. Okay, so the problem with this thing is that you can't compute it because there's infinity here, right? It's going to be very hard to write any program that effectively computes it. So we want to cut down the size of this invariant. How are we going to do that? I'm going to define the following. So I'm going to fix a field, okay, f, and now what I'm going to do is I'm going to define a vector space Cn. So this is a vector space with bases given by all maps from I1 to the box power of n into X. So X is a graph, and I'm defining, I'm taking just this huge number of these maps, and I'm not going to take all of them. So what does that look like? Okay, so this is n equals 0, that's a point. N equal 1, that's a line. N equal to 2, that's a square. And then I get a cube, and then I get higher dimensional, like all the hypercube graphs. Okay, so a different notation for it would be Qn. Now, I'm not going to take all of them. I'm going to only take those that are non-degenerate. So this thing has kind of n directions. So here I have direction 1 and 2. Here I have 1, 2, and 3. 1, 2, and 3, and so on. And so I can take, I can fix a direction, and I can essentially take the top or the bottom. So for direction 1, this is the bottom face here, and there's a top face here. For direction 2, there's the left face and the right face. For direction 3, there's front and there's back. right? And so I'm going to say that this box n to x is degenerate if maybe I'll call it di di 0 of f is equal to di 1 of f. So di 0 of f is like the beginning in one direction, and di 1 of f is the end, right? So maybe to make it clear in this case, if this is my cube f, then this side would be d2 0 of f. This would be d2 1 of f. This would be d1 0 of f and d1 1 of f. Okay. So I'm taking those that are non-degenerate. So where this thing is not equal to this thing. Okay. That's what it means for a cube in my graph to be degenerate. And okay. Why should you be interested? So I can arrange all those different Cn's into a sequence like this, Cn minus 2, and so on, with maps that I'll call this partial. And partial on such a cube, on such a map F, like if I want to define something on a vector space, I just tell you what it is on this basis. It's going to be sum of di epsilon f. I need to put -1 to I plus epsilon, and this is over all I and all epsilon. Okay, one thing you can check is that if I do this d twice, so this is, if I do, maybe I'll give them indices. So if I do dn minus 1 dn, that will be 0. And a different way of saying it is that the image of delta n is contained in the kernel of delta n minus 1. So I can try to measure the difference between those two. And this is what I would call the the nth homology of a graph X with coefficients in F. I'll define as the kernel of delta n quotiented by the image of delta n minus 1. Okay, that's a definition. That's now a finite thing that you can compute, right? Like you can compute all the graph maps. That's a simple condition you can check. And then you compute these differentials. And okay, for this, there's like Smith normal form that tells you how to compute it. So now you can run these computations, and instead of these invariants that's like maps from an infinite line to C5, you can try to compute this. And these see essentially almost the same information as these A groups, and they again detect large holes in your graph. Every computation that I showed here would pretty much come out the same. Like for this one, I would need to be careful about the choice of the field, but essentially you can detect everything you have here. Okay, so this is something that we really want to compute. Okay. Okay, so that's something you can do. And what that lets you do essentially is identify large holes in your graph. So why would you care about it? Like, let me give you, let me just give you very quickly. Okay, so one thing that we did with this, for instance, is we look at weather data from many different places, and you can essentially see for any two places, you can see how weather in this place correlates with some other place. Like for any pair, you can do that, but maybe you can't correlate it three ways, right? Like you can get R squared for three different places. You only get the R value for two fixed places. Do it for all things that gives you like you can see how they correlate based on the R-squared value, and that gives you some filtration of graphs as you vary R, right? Like the edge is there if your R-squared value is at least this. Okay, so then we took this data for North America and checked what we got. The generators of this homology group detected lakes and mountains. Exactly. So these are the large holes that we're able to detect. Now, of course, that's useless, right? That's more of a proof of concept because, yeah, there's no weather station in the middle of a lake. So of course it's going to be, but then we thought, okay, let's do it differently. Let's not look on top, let's look below the surface of the Earth. You can look at seismic data, and you can detect exactly where there could be developing activity that could lead to something like an earthquake going forward.
But you're not using the geometry. You're ignoring the geometry in that case, right? For these problems.
So, well, no, so what this does for me is I can...
But you're looking at the graph.
Right.
Stripped of geometric information, right?
Right. So essentially what I'm trying to convince you of is that these groups detect the geometry. They detect those large holes. So when I'm given this data, I only see a bunch of numbers. I forgot all the geometry. And this is a way of getting the geometry back from just a graph, right? So computing this, like I know this is like a lot to take in at once, but this algorithm, like this construction is extremely, is in my mind, actually, like if you just spend a little bit of time, this is a relatively simple construction, but it's very hard to compute. And what we would like to do is we would like to figure out ways of, for instance, like, can we look at fewer maps here? Like we figure out that, okay, maybe you don't have to, you can look at the smaller set of maps and it will still give you the same homology. But one thing that I would love for people who know way more about this stuff than I do is to essentially find effective ways of computing this, because clearly there is stuff there that tells you something about, healthcare data, seismic data, weather data, stock market data, and we can't compute it on like larger examples.
So you want to respond? I think if you formalize not this question, but the question of finding large holes, you'll find that if it's of finite size, then there is a fast, efficient algorithm for doing it. And if it is arbitrary, is it unbounded part of the input, then it is NP-hard. So either even if you could solve this problem, it would only be, presumably, it would only be a heuristic unless you're proving P is equal to NP.
Yes, I'm not planning on that.
Yeah, good.
Right, but
if you're asking a computational problem.
yeah, so I'm not asking for a universal algorithm necessarily, right? But I think, I think what I would like is at least a heuristic that would let me, like you can do some simple things with your graph. I'll just give you one example of a. Right, so let's say you have some graph here. I don't want to think about it, but let's say that it has one edge sticking out, right? Well, if this is the case, you can just remove this edge and generate way fewer maps. Like it's homotopy equivalence. You're going to get the same homology. So that can always be removed from a graph, right? You can, you can come up with other things. Like if you have a vertex such that all of its neighbors are contained in the neighbors of another graph, then you can also remove that. And I feel like there ought to be some way of turning this question into a question of some discrete Morse theory or like elementary collapses that would let us compute it more efficiently. But we don't have a good way of doing it. So that's why I want to talk to people who actually know things like this and can help me. Okay, I think like oh my God. Okay.
I think-